In the last video, we saw how we can start with a concrete problem. So both the problem and its desired solution may be expressed nicely in terms of certain concrete steps. However, moving from the problem to the solution is not easy in the concrete version. So this is possible but not easy. Like counting up to 1,000 using the pillars, or carrying out that long parade command for the soldier. However, we can convert this problem to a problem which is more abstract in the following way. So from this problem we will go up into an abstract world. So we shall ask an abstract question. Then instead of moving in the concrete world, we will move in the abstract world to an answer. And this often is easier than this. And then we shall come down, we shall retranslate that answer back in terms of the concrete problem, and that will provide us a solution to our original problem. So this is the core idea behind any kind of abstract algebra. And I have also mentioned that the same abstraction often underlies different concrete problems. We have already seen the same idea even in our early school days or even in our preschool days. For example, if I ask you that there are 3 apples and I give you 2 more apples, then how many apples do you have? If you ask this question to a child, the child will follow the concrete path. That is 1, 2, 3, then this is 1, 2. The child will actually put the apples together and count 1, 2, 3, 4, 5. And he will answer that there are 5 apples. Now you ask the same question again, but in terms of bananas. And the child will again go like this. 1, 2, 3, 1, 2. Put them together. 1, 2, 3, 4, 5. If you ask the same question in terms of orange, then you will see that the child is again counting right from the beginning. That is the concrete way of doing things. But after doing this again and again, we understand that the fact that we are working with apples here and bananas here does not matter at all. So we eventually learn to think of just that abstract property of this bunch of apples that matters, and we call that the number 3. Similarly here we call it the number 2, and put them together and count. This becomes an operation which we call addition. So instead of saying this many apples and this many apples together give me 5 apples, we write 3 plus 2 is equal to 5. That is something which is abstract. Now, the same abstraction underlies both apples as well as bananas. That hardly comes as a surprise to us adults. But there are other things which also may be modeled using this. For example, traveling a distance. So if you travel a distance of 3 units and then follow it up by traveling 2 more units in the same direction, then again the answer is 3 plus 2 equal to 5. If I have 3 apples and I take away 2 of them, I am left with 1. Similar thing about bananas and oranges. But in case of this traveling, now it is somewhat strange. If you move in a direction and then you move back in the opposite direction, then that may be modeled in terms of subtraction. So these addition and subtractions are nothing but useful abstraction of different concrete operations. And that is why we learn these things, because there are so many concrete things around us that may be modeled using those basic operations. In case of abstract algebra, naturally, we want to come up with even more such basic operations, because whenever we are in a concrete world, we do things step by step, like counting 1, 2, 3, 4, all those 1000 numbers in those 7 pillars, or all the instructions in the parade, or turning the cups over. So we are doing things step by step. And every time we do the step, the state of the problem changes. So every time I move one more step, my distance from the original point changes, goes up or goes down. And we need some operation to express that. So when I want to do an abstraction, I basically create an abstract operation which will express that concrete thing. Now we do things one by one. That's how we human beings always work. So I can say I have done something, I have a configuration to which I do the next thing, to which I do the next thing. So at every step we are combining two things at a time. As a result, the operation that we care about is called a binary operation. Nothing to do with binary number. Binary means an operation that combines two objects into one object, like 3 plus 2. The two objects were the two numbers, that was 5. Similarly, in the example of the parading soldier, when I said left, that is one object, and if I now say left, left, then one step following the other, we may not use any symbol for that, but there are two things. So the two things combined, you can easily feel that if the soldier is facing in some direction right now, it's like this, you say left, so the soldier now faces this, another left, the soldier now faces this. So compared to the original position, the soldier has actually made an about turn. So L followed by L is an about turn. So I will write it like this. L followed by L is same as an about turn, which I denoted by A, I think. Now this followed by is a concrete thing, because we are working with soldiers. Now just as we use this notation plus, which has nothing to do with putting things together, it is just an abstract symbol. Similarly, here also we will often replace it by an abstract symbol. We might use the same plus, or we might use something which I have not used. Say I write star, or you can write a heart symbol, whatever. Use something. L followed by L is same as A. That is a binary operation. Just as when we work with addition, we learn about the rules of addition, like 2 plus 3 is 5, 5 plus 7 is 12, and things like that. And similarly, when we learn multiplication, we memorize the multiplication table. Similarly, for any binary operation, we can have a table, like a multiplication table. So in this case, I have shown the multiplication table or the binary operation table, which I have fancifully denoted by a heart. You can use any symbol. And so this, what it says is this: suppose the first command is this and the next command is this, then what is the composite command? For example, let's take this. I said that the first command is A and it is followed by the command L, then the overall effect is that of R. So let's understand. Suppose the soldier is facing like this. So after an about turn, the soldier will now face like this. turns around, and from this there is a left command. So the now soldier is facing like this. So remember, the left is with respect to the current position of the soldier. So this is where the facing, and towards left, so it faces like this. So effectively you start with this and you end up like this, and that is a right. So wherever the soldier starts from, an A followed by an L is R. So we will say A followed by L is equal to R. And similarly, we get this entire table. You can just check for yourself that the other entries are also given like this. For example, halt means just continue facing in whichever direction you are. As a result, halt does not change anything. Halt followed by left is left. Halt followed by A is A. So halt does not change anything. So these are the various things. Now we have already noticed when we discussed this particular problem in the last video that it is possible to express the same thing in a slightly different, more familiar way, like this. Instead of calling these numbers, calling these things as H, L, A, R, you might as well consider them as the number 0, 1, 2, and -1. Similarly, this is 0, 1, 2, and -1. In that case, this operation may be done mathematically in the following way. Suppose 2 plus 1 makes R, which is 2 plus 1 is 3. How come that becomes -1? The operation is simply this, that you are doing things modulo 4. And it will help if instead of -1 you consider this as 3. That will be better. So now it is 1 plus 2 is equal to 3. Now let's take another example. Let's take this. 3 plus 1 is 8. That is 3 plus 1 equal to 0. So this operation is actually modulo 4. That is, you do 3, add 1, and do this addition modulo 4. That is, you divide by 4 and take the remainder. That will indeed be 0. So this binary operation may be considered to be the same as the binary operation adding modulo 4 if you encode H as 0, L as 1, A as 2, and R as 3. In abstract algebra, we work with binary operations in an abstract way. Now, sometimes abstraction becomes too much for our nerves, and it helps if we think of them in terms of some concrete representations. Just like if you try to teach addition to a child, it will be very difficult for the child to just remember in an abstract way 2 plus 3 makes 5. Instead, it will help if you actually give the child 2 marbles followed by 3 more marbles, ask the child to count up the entire lot and obtain the number 5 for herself. Then it becomes natural. So we human beings like to live in a concrete world. Abstraction is a secondary thing that helps. So just dealing with abstraction in an abstract way, that usually is very boring. So the example that I am now going to give you is designed to add a dash of concreteness to abstraction, and this is an example that you will find useful even later in this class. So for this, it will be a good idea if you do it yourself. You take a cardboard triangle, an equilateral triangle, where I have labeled its vertices with the numbers 1, 2, 3 on both sides. So I hold it on some flat surface, so 1, 2, 3. Now I will make the outline. So I will make the outline of this on the board, and I will label the vertices of the outline with the same numbers 1, 2, and 3. Now what I am going to do is very much like that soldier parading example. This is my soldier and this is the parading ground. So if I give the command left, then the soldier will turn not by 90 degree but by 120 degree and will fit this. Because it's an equilateral triangle, even if you turn it by an amount of multiple of 120 degree, it will be there. So now you can see 1 goes to 2, 3 comes to 1 and 2 goes to 3. So initially it was 1 with 1, 2 with 2 and 3 with 3. Once I turn it like this, now it is 3 to 1, 2 goes to 3 and 1 goes to 2. And I can again rotate it further. So I will get to this thing. Or I can rotate it like this. So here are the different ways by which I can take this triangle and put it back such that it fits again into the same space. Now if you think for a moment, you will see that the operations that I can do are the following. I can of course do nothing, that is our halt, what I call halt. In this case, I will call it by the letter E. No reason why I am using E, I could have used any letter. So E stands for don't do anything. That is the simplest of them all, so it is this. Or I can do a left turn, so I will call it left. So when I am writing these are abstract objects. They do not really have to have a meaning, but I am giving you a meaning so that you see the binary operation in a concrete way. If you are confused, you can actually do the concrete thing and check whether you are doing the right thing or not. So that is L. Similarly, I can do it this way, that will be right. And I can do more exotic things like I can flip it around. For the soldier, of course, we could not flip the soldier around. That would amount to making him stand on his head during the parade. Impossible. But here I can make it to a flip. So I am flipping in this way. Suppose I say I am going to flip in this, so along this vertical axis. So I will call it F1. So when I say F1, wherever I have 1, I am flipping it centered at this. Similarly, I can have F2, flipping it like this. So if I start with this, flip 2 will make it flip like this. Similarly, I flip 3, it will make it flip like this, F3. So I have got 6 such ways by which I can take this thing up and change it and put it back. So these are the basic parading commands for my triangle. And again, my binary operation will be do one after the other. And let's see whether we can come up with certain operations. So I will again denote it by, say, the heart symbol. So L heart R means L followed by R. Let us see what I will get. I know that I must get one of these 6 because if after the first operation it fits and after the second operation also fits, then if you do both the operations, it will continue to fit. And if it has to fit here, the net result must be one of these 6 because these are the only 6 operations that I can carry out on the triangle such that it fits back into its original position. So let's see what happens. So I will start with some configuration. Doesn't matter what I start with. Suppose I start with the thing 1, 1, 2, 2, 3, 3. I do a left and then I do a right from this. So clearly they cancel each other out and it will be E. So let's do something more esoteric. Say I do F1 and I follow it up with F2. What happens then? Let's see. So if I ask you what happens, then it is difficult for you to figure out. So that's why the concrete example. This I do F1 and then I do F2, that is along this, I do this. You not see the effect that has happened? I was originally like this. Finally, I have become like this. So that is nothing but R. So this combined with this will give me R. And it's a good exercise at this point to write down the entire multiplication table, if I may call it. This is not multiplication. This is a new thing. So write down the new heart table or this table for the entire binary operation and see what you are getting. And it will be interesting to see if F heart F2, F1 heart F2 is same as F2 heart F1. So you can try to see whether this is also same as R or not, and let me know about your answer in the comment box. And in the next video, we shall continue to explore properties of such binary operations.